Hello and welcome to Biorules video lessons. So carry on our revision on chemistry for biology. Let's talk about hydrogen bonds today. So for us to talk about hydrogen bonds, we have to talk about the water molecule. We saw in the revision last class that water molecules, they are made by one oxygen, two hydrogens by covalent bonds. One oxygen is sharing electrons with two hydrogens. Each of these covalent bonds is sharing two electrons. So there they are, they're going to be happy. Now, 8 protons in the nucleus of the oxygen, 1 proton in the nucleus of each hydrogen, and they have electrons being shared between them. I'm representing here only the electrons that are being shared in the covalent bonds. So we have 2 electrons shared with the hydrogen on the left, and we have 2 electrons shared with the hydrogen on the right. So what's going to be happening here? These electrons are going to be shared, so they are going to be flying around. They go over there. You can see here that they fly around the oxygen, they fly around the hydrogen, and they are there, happily flying around. So they are in both places. This is the definition of covalent bonds. They can be with both atoms, so they are shared. So both atoms now have the fair share of electrons. Okay, but there's a question regarding this. Negatively charged electrons, they fly around the positive charge, okay, nucleus. The problem is there are 8 positive charges in the nucleus of the oxygen, and there is only 1 in the nucleus of the hydrogen. So are these guys going to be flying around evenly? So just to show you, that goes, you see, oh no, it's not going back there, oh no, yeah, it's staying a little bit more over here, okay, oh, it's staying. So you can see here that the electron likes to stay around the oxygen a little bit longer, then it likes going to the hydrogen. Of course, you're saying like here, but it's not a matter of liking, it's a matter of ending up to be, because there are more positive charges. So the natural tendency is going to be for the electrons to spend more time around the oxygen than it spends around the hydrogen. So in theory, those are all happy. They have the electrons flying around the last shell in the number that they are supposed to be. The hydrogens are happy because they have 2 electrons flying around them. But in reality, they don't spend the same amount of time with them. So actually these electrons are shared, but not evenly shared. They spend more time in the oxygen than they spend in the hydrogen. So the answer for that question is no. Okay? The electrons tend to orbit more the atom that has a higher positive charge. So in this example here, okay? So it spends more time in the oxygen, okay? As a result, the oxygen now contains electrons flying around it, but it should be 8 electrons on the average flying around it, so the electron should be here or there, so it should be 8 electrons flying around the oxygen, but as a tendency, the electrons spend a little bit more time around the oxygen, so it's a little bit more than 8 electrons spending time there. As a result, the oxygen tends to have a slightly negative charge, and the hydrogen have electrons fly around it, should be 2 electrons fly around it, on the average should be 1 electron. No, 1 is here, no, the other one is there. Now 1 is here, the other one is there. Oh yeah, let's spend time in your mother's house. Okay, but I'll spend time in my father's house. Oh, okay, but in the end, they like more one than the other. So in the end, they spend more time in the oxygen, so the hydrogen end up having less than 1 electron on the average fly around it. So as a result, the hydrogens are slightly positive. So if they are slightly positive, slightly negative, they make charges. These molecules are polarized because they have poles. They have negative poles, they have positive poles. These molecules that are going to be polarized. So that's what we have here. This is the overall charge, is slightly positive in the hydrogen side, is slightly negative in the oxygen side. So why is this important? This is important because if we put a a water molecule together of another water molecule, they are going to be facing each other, and they will end up making a hydrogen bond. We represent a hydrogen bond by a dashed line. It's this slightly positive charge being attracted by this slightly negative charge. This is the idea of a hydrogen bond. What we have here is now five actually, sorry, one is in the middle, 5 water molecules, and they are being connected by hydrogen bonds. You see those dashed lines over there? They are representing hydrogen bonds. So we have the positive side, hydrogen side facing the oxygen, hydrogen facing the oxygen, oxygen facing the hydrogen, oxygen facing hydrogen. So water molecules, they tend to get kind of attached to each other by a hydrogen bond. They have a certain connection between them. And this will be very important for water molecules. So here, another example, water molecules being connected by hydrogen bonds together. Sorry. And they are going to have this special bond. This will make water molecules to be very cohesive, to be very, attached to each other, and this will give many important properties for water that we are going to be seeing in another class. Hydrogen bonds doesn't happen only between water molecules. It doesn't even happen only between hydrogen. It's called hydrogen bond because that's the typical one, okay, when the hydrogen, but it may happen with other elements as well. So in this case here, it's happened between the nitrogen that's slightly more negative and the hydrogen of the oxygen is slightly more positive. So this here is a water and ammonia hydrogen bonds. So now we can have hydrogen bonds in different possibilities. Here in this example, we have hydrogen bonds represented in nucleic acids. This is the thymine and the adenine, the T and the A of DNA, and this is the C and the G for DNA. And they are making hydrogen bonds. Thymine and adenine can make 2 hydrogen bonds between them, and cytosine and guanine can make 3 hydrogen bonds between them. So not only between water, not only between water and ammonia, actually we can have in many molecules, for example in nucleic acids, DNA, RNA, they are capable of making hydrogen bonds as well. Just to illustrate, molecules like water that are polar and can make hydrogen bonds, they tend to have a much higher point of evaporation, or the ebullition here, the gasification temperature, compared to other molecules, like in this case here you have apolar molecules that are going to be vaporizing at much lower temperature. You'll see more of this next class. This is just to give you a little bit of a taste that water, for being polar and making hydrogen bonds, the molecule tries to stick together, so it needs much more heat, much higher temperature to be able to put them in the form of gases and making them to evaporate. Okay. Here, for example, boiling point of methane. Methane is a CH4, very similar in mass to water, and the boiling point is it's very negative, less than 100 degrees Celsius negative, while water, the boiling point is 100 degrees Celsius positive. All the way over there, water is all the way over there. So very similar molecules, water and methane. The water has a much higher boiling point than the methane because you need much more energy to be able to boil it in comparison to the methane, which is an apolar molecule that doesn't connect to each other by hydrogen bonds. Okay? I hope you had enjoyed this revision, reminded yourselves of chemistry, and I'll see you in the next class. Take your time to do the quiz. Bye bye.